Okay, so today I want to talk about the basic elements underlying Mathematica, those being lists, functions, and strings. So I'm going to talk about what they are, how to manipulate them, and how to combine them. And I think it's going to be a very interesting tutorial. And I'm going to talk about lots of examples. This picture here shows riffle shuffling of a deck of cards, and I'll show you how to program this within like one line of code. So, hope you're going to enjoy the tutorial. Let's get started. The concept of lists is really one of the most fundamental ideas in Mathematica. So, to make a list, you use curly brackets and you put in the elements of your list separated by commas. Now, to evaluate a command in Mathematica, you hold Shift and press Enter. The important thing to understand, though, is that the elements within a list can be anything. They can be numbers, but they can also be letters, combinations of letters. They can even be pictures. For example, suppose I want to attach an image of myself into this list. I can do this using the current image command. It will get a snapshot from my webcam. There I am. And we can take this list and we can give it a name. So for example, we might want to call it my list. Now, since we've given this thing a name, we can now do operations on it. So for example, we might consider what my list plus 1 is. And here we see we have added 1 to each of the entries within this list. Okay, so there are various different ways which we can generate lists. Another way we can generate lists, rather than just typing them out manually, is to use a command like this, range eight. That will give us all the integers from 1 to 8. Or we could say range 3 to 8. That will give us the integers from 3 to 8. Now, another thing which is very important, of course, is how do you actually get at the entries within a given list? So let's say we want to know what the third entry is in my list. Well, we do that by using double square brackets. And there we have it. The third entry in my list is cat. And also notice that the output here of my list can be used as input. So if we just go to this and press space, we have this cat thing here. We can add 1 to it or whatever, and we get cat plus 1 because cat has not been given a particular value yet. So Mathematica just treats it as this kind of unspecified variable. Okay then, so let's talk about some more ways to generate lists. I've already shown you how to make the integers from 1 to 8 like this. Here's another way to do it. We can make a table of I where I goes from 1 to 8. Okay, so this does pretty much the same thing. It's a little bit clumsier in some sense because we have this kind of dummy variable I here. I mean, we could just as easily have used J or any other combination of letters here. Now, maybe we don't want to get all of the integers from 1 to 8. Maybe we only want to say get every other integer. So in that case, perhaps we could just put a 2 here. And then we go up in steps of 2 until we get to the largest number, which is less than or equal to 8. So in this case, we get 1357. Another thing we might want to do is perhaps just go up in increments of, say, 0.2. So now we get a rather longer list where we keep adding 0.2 until we get all the way up to 8. Okay then, so Mathematica also contains a random number generator. So for example, if we type in random integer from 1 to 6, it's a little bit like rolling a dice. It'll give us a random number between 1 and 6, generated randomly each time. Now, what we can also do is make a list of random numbers. Say we want a list of 10 random integers from 1 to 6. We can just put a 10 here. So let's do some experiments with probability. Let's call this list dice rolls. Okay, so let's now evaluate what the mean of this list is. Notice that this mean here is a built-in function of Mathematica, and as usual in Mathematica, you use single square brackets to enclose the input of a function. So mean is a built-in function. We use square brackets and put the name of our table inside, and we get that the mean in this case is 4. Okay, let's do it again. This time the mean is 17 divided by 5. Well, that's not particularly easy to interpret, so what we could do is put 1.0 times this, and then it'll give us the output in a more digital fashion. Okay then, so to do our experiment in probability, let's do a few more dice rolls. Instead of doing 10, why don't we do 10 million? Okay, so if I just evaluate this command, then it's going to give us a list of 10 million random integers, and that's going to look quite messy. So what we can do is put a semicolon here. Now this just sort of silences the output, so the function will still be evaluated. It's just that we're not going to actually see what gets made. So there we are. Now if we do this again, you see that we get an answer which is much closer to the value 3.5, which is the value you'd expect to get when you're rolling a lot of dice. This would be the average value you should get. Okay then, so now let's talk about how to make some more elaborate lists. Suppose we want to list the squares of the first 8 positive integers. Well, one way we could do it is like this. We could say table, use a dummy variable I, hat means to the power of 2, and we let I run from 1 to 8. Okay, so we could give that a name. Maybe we call it squares. And there we go. Now, it's important to realize that there are many ways that one can generate this kind of thing. So let's make another list. We'll call it up to 8. And that's just going to be equal to the range of numbers from 1 to 8. Okay? So now I'm going to show you one of the most important commands in Mathematica for manipulating tables. It's called map. Okay? So if we say map F A B C, then we get a rather nice kind of illustration of what this command actually does. Because Mathematica has no problem with dealing with things in a completely symbolic way. So if you want to understand what certain functions do, you can often just type them in with letters instead of numbers. And Mathematica will sort of show you what a command does. Now, let me show you this map command in action now. We use this command, and what map does, rather predictably, is it applies a function to a list. So what function are we going to apply? Well, we want to square the numbers. So we want to specify the square function. And here's how we do it. Hash to the power of 2 ampersand. Okay? And then we put the thing we want to operate on, the list we want to operate on, which is up to 8. And evaluate. And there we have it. Again, the squares from 1 to 8. Now, this is the usual kind of syntax that you use in Mathematica. It's dummy free, but to represent the kind of input variable, we use this hash. And then we use an ampersand to close the kind of function. Basically, this represents that you've stopped talking about the function now. So, just for example, say we want to get back to where we started from. We could say map. Now, actually, there's a built-in square root function in Mathematica. So, square root of hash, ampersand. We're operating on this list. And there we are, back to base. Okay then, so that's some ways you can make interesting lists. How about visualizing lists? Well, a fairly simple way to do that is to use list plot. So you just use list plot and then put the things that you want to list. Now, list plot has millions of added features. Just for example, you can join the thing. And you can also plot various different lists. So you can compare things. Okay then, so another very, very useful command, pretty simple, is length. So length just gives you the number of elements in a particular table. So for example, squares has 8 entries, so the length of squares is 8. Okay, now I want to show you a much more interesting kind of way of generating lists. It's called nest list. Now the idea of this is that you keep applying a function starting from a given input a certain number of times. So Mathematica here is symbolically showing us what it's doing. So if our function is f and our input is a, then we apply this function f to a total of 5 times, and we list the things we get when we apply the function once, twice, thrice, and so on. Okay, so let's do a practical example. Nest list. Say we want to times by 2. So again, we specify our function using hash in a similar way to we did with the mapping command, map. So we go hash asterisk 2, that means times the number by 2. We close our discussion of the function with an ampersand. Let's say we want to start with 1. and we want to do this for 5 steps. So what this says essentially is start with 1 and keep multiplying by 2, a total of 5 times, and make a list of the things that you get. So let's execute this, and there we go. Another very useful command in a similar vein, but perhaps more powerful, is nest while list. So here we again can put in a function. Let's do times 2 again. And again we can put an input. And now we can also put a certain specification. So for example, keep applying this function just so long as this particular statement remains true, that the number which we're using is less than or equal to, let's say, 129. Okay, and this is what we get. So you see what's happening here is we're keeping multiplying by 2 just so long as our number which we're operating with is less than or equal to 129. Now as soon as that's no longer true, we kind of stop doing what we're doing. So this is actually an extremely powerful thing, and you can probably already see that you can combine these things together to make some very, very powerful commands. Okay, so these curly brackets denote these lists. Now, of course, the order of these lists are important, and essentially, if you're speaking about mathematics, you can think of these like vectors. So for example, if lists have the same length, you can add them together, and it just adds them component-wise. Now, also in mathematics, you tend to represent sets with curly brackets, and sets are kind of like lists where the order doesn't matter. Now, Mathematica is very flexible, and you can actually think of these things as sets as well, if you want. And the usual set theoretic operations are again built into Mathematica. So you could consider, for example, the union of 1, 2, 3 and 3 and 4. And this is going to give us the set of all things which are either in 1, 2, 3 or in 3, 4. And so there we have it. And we also have an intersection command. This gives us the set of all elements which are common to these two sets. So in this case, 3 is the only common element. And in this case here, there are no common elements. And we also have this command here, which gives us the list of all subsets of a given set. Okay, so union and intersection are a couple of ways that you can take a couple of lists and make a new list. Another very common method is join. So that very simply just sticks together a pair of lists. And that's obviously a very useful command. Now, another thing you can do is riffle. This is more rarely used, but can be a useful shortcut sometimes. Okay then, so let's have some fun now. Let's simulate some card shuffling. So let's generate, let's say, a 10 card deck. So this list here of integers from 1 to 10 is going to represent our cards. Now, there's a couple more functions I need to tell you about. One of them is take. Take simply takes the first so many elements off the front of a list. So for example, take 3, takes the first 3 elements from our list. Similarly, kind of oppositely, if you like, drops the first so many elements off the front of a list. Okay, so how are we going to simulate our card shuffling? Well, how do you shuffle cards? Well, one way to do it is a riffle shuffle, where you split the deck of cards in half. So you take one half in one hand and one half in the other, and then you riffle them together, and you repeat that process. So let's do that repeatedly. So nest list. Now we're going to specify what we're going to do. So we want to do a riffle shuffle, and we want to take our deck of cards and take the first 5 in, say, our left hand. And we also want to get the thing we get by discarding the first 5 in our right hand. And we want to riffle shuffle those together. And we want to operate on this list here. And let's say we're going to operate on it 10 times. There we have it. So let's make a visualization of this. We can use a command called array plot. And make it look a bit more pretty. Okay, so there we have it. In fact, if we want something a bit more interesting, we could do it with, let's say, a 52 card deck. And you see that there's some fairly interesting fractals going on here. Okay then. So this is a kind of visualization of card shuffling, where different colours are representing different numbers. But anyway, I won't get too distracted by this. Let's just say that array plot is a way of visualizing a sort of matrix of numbers. So, for example, if we want to specify a matrix, that's basically a list of lists. So here's a 2 by 2 matrix. If you want to see it in a more familiar form, you can do this. Now it looks a bit more like a kind of mathematical matrix. Anyhow, we can do an array plot of this. And basically, the first row of this represents the elements 1 and 2, and the second row represents 3 and 4. And the darker the square represents the higher numbers. Okay, so now we're going to sort of sidestep and talk about functions. So functions are really important things in Mathematica as well. And I've shown you a few different built-in functions. For example, square root. But you can also define your own functions. So let's say we want to define a function which multiplies by 2 and adds 1. It's fairly easy to do. There's actually a couple of ways you can do it. Like most things in Mathematica, you can do it using dummy variables, or you can do it without using any dummy variables, using a hash instead. So here's using dummy variables. We'll use x. So we have to put a colon here, and then the output is times 2, 2x plus 1. So x goes in. We put this underscore here to represent that this is an input, and the colon here, and then this is the output, times 2 plus 1. So let's just check that it works. Yeah, that's good. Now, equally, we could specify it in a different way. Well, let's call it something different. Let's just call it function. And we could say that it's equal to the input multiplied by 2 plus 1, ampersand represents the end of the function. So again, we get the same kind of thing defined. I must say I think that this form of programming is preferable because, one, it avoids using dummy variables, which are kind of introducing meaningless information into your code in some sense, and two, it makes your code shorter, and because of the way Mathematica is, it's much more difficult to actually go wrong when you're coding because you'll easily see if the parentheses don't tie up or something like that. Anyway, so we've got our times to add 1 function. Now let me show you one of the most useful functions in Mathematica, and that's the if function. So if, and then some criteria. So let's make a function. Test if input is 7. Okay? So if, okay, so the input here, let's call the input what? Doesn't really matter what we call it. So if this is equal to 7, notice that we have to give a double equals here. Then this function returns 1, and otherwise it returns a 0. Okay? So let's just check that this function works. So if we put 6.9999, we get a 0. But if we put 7 in, then we get a 1. Okay, so this if command is very, very useful. You can use it with inequalities and all sorts. And when you think about how you can use it in conjunction with things like nest, you can really do some very, very elaborate things. Okay, so another pretty useful function is mod. So this might be familiar to the mathematicians amongst you. It's easiest to show you how mod works if we just apply it to, so let's do mod 5. Let's just apply this as a mapping. To the integers from 1 to 9. Okay, so this is our input, and we're going to apply this mod to each of these things. Actually, let's go from 1 to 30 instead. Okay, so what we're doing here essentially is getting the remainder when we divide the number by 5. In fact, just to make it a bit more clear, let's list the actual number followed by what we get when we do this mod thing on it. Okay, so for example, when we try to divide 21 by 5, we're left with a remainder of 1. Therefore, mod of 21, 5 equals 1. We're going to make a function called Collatz, and it's a function of x and y. And it works like this. If x is equal to 3 times y, or x is equal to 2 times y plus 1, or, okay, so these double vertical lines represent logical OR. So we want it to be a symmetric function. So we can just put these things in with the entries swapped around. So if any of those conditions hold, then we output a 1. Otherwise we output a 0. Okay? So that's our function. We're going to use that to make an interesting looking network. Now, what we're going to do first is there's another way of making lists which I haven't shown you yet. It's called array. And so you use this hash ampersand style notation. And you see that it's kind of similar to the table command. The difference is that it doesn't have a dummy variable in it. So in a way it's kind of like cleaner. And also it generalizes, so you can have multi-dimensional arrays. In other words, you can make lists of lists quite easily. For example, here we have a list of 4 lists of 4. Now, another thing you can do here when you're making one of these two-dimensional arrays is you can let hash 1 represent the kind of first coordinates. So essentially you're like building a matrix. So hash 1 is like the first matrix entry, the first index, and hash 2 is the second index. So for example, you could define hash 1 plus 2 times hash 2. That could be a function. And you could make, let's say, a 4 by 4 matrix based on that. So for example, here we have that this is where hash 1 equals 1 and hash 2 equals 2. So it's 2 times 2 plus 1, which is 5. Okay then, so now we can use all this stuff to make something pretty interesting happen. Okay, so if we type array of Collatz hash 1 hash 2, let's say the first 20 thingies. We'll do a 20 by 20 array. So we get a binary array out. Now, let's visualize this. We can think of this as an adjacency matrix for a graph. Now, if you don't know what that means, don't worry. Just you'll understand in a second. So we do adjacency graph of this, and this is what we get. So actually, let's make this graph a bit bigger because it's kind of interesting. Okay, and here we have an interesting network which is defined by this Collatz function. So to see more about this, if we right click on it and go graph style, we say small network. Okay then, let's make this a bit larger. So hopefully you can see that a pair of entries are linked, a pair of numbers are linked in this graph if either one is equal to 3 times the other. Like for example, here we have 7 is linked to 21 because 3 times 7 is 21. Or if 2 times something plus 1 is equal to the other. For example, 2 is linked to 5 because 2 times 2 plus 1 is 5. Okay, so actually this is pretty interesting because this is a kind of graphical representation of a famous conjecture in mathematics called the Collatz Conjecture, which I'm not going to go into too much. But suffice to say, if we look at this thing on, let's say, 150 vertices, we get a fairly interesting looking network. And just for fun, I can't stop myself, I do a graph plot in 3D. And we get this nice kind of three-dimensional rendering of this network. But anyway, you can see the full talk on how to make networks in Mathematica. I'll go into these topics in more detail. Okay then, so let me just show you a couple more things about lists, in particular about how to pick out certain elements of lists. And then we'll go on to talking about strings, and then we'll wrap up because that pretty much finishes our tour of the simplest stuff in Mathematica. So okay, let's have a look. Let's generate a list. Range, let's take, I don't know, the first 100. And we're going to take these first 100 integers mod 7. Okay. So let's say we want to know what indexes the 6's occur at. So for that, we can just type position of this list and then 6. And we get the different entries where 6 occurs. And of course, they're separated by 7, as they should be. I find it a little bit annoying sometimes that Mathematica gives you the output in this fashion. Usually I have to apply this function to it. And that gives you it in a sort of cleaner output. Okay, another fairly useful function while we're on the topic of cleaning up lists. Say you have something like this and you want to get rid of all the brackets inside, you can use flatten. That gets rid of it, and you can make flatten more precise. Like you can look it up on the help menu. Another really useful command is select. So you select from a list with a given criteria met. So let's get all the numbers from 1 to 10 that are divisible by 3. So that would mean mod of a thing of 3 is equal to 0. Okay, so we get all the numbers from 1 to 10 which have a remainder of 0 when divided by 3. Okay, another really useful command, well, I'm just sort of blitzing through these. So random real generates real numbers, let's say between 0 and 1. Let's say we generate 7 of those. And so we can sort them. We can sort them so that, let's say, the first entry, the preceding entry is always greater than or equal to the succeeding entry. So we've sorted these numbers in sort of decreasing order. And you can put any conditions you like in here. So this can be an incredibly powerful way of manipulating lists when you put the right kind of functions here. Okay then, so that's pretty much all I want to say about lists. Now let's go on to strings. It's pretty much the last thing I want to talk about. So the way you specify a string is with these speech marks. So this is a string. And the great thing about strings is that there's a whole different sort of set of commands for manipulating strings. And you can convert between strings and lists and expressions and stuff really easily. So one thing that strings are really useful for is if you have some kind of data or some kind of mathematical expression which is in some kind of form, then you can always use some really primitive string manipulation to like convert the forms of stuff. Okay, so one really useful thing is string join. So for example, we could join the strings dog and fish. We get dogfish. Okay. Also, you can convert things to strings. So, for example, here's a Mathematica expression. Now, if you just type toString, you can see that it's now a string. So, this toString command allows us to convert expressions into strings. Now, we can go back the other way by using a command called toExpression, which just gets us back to an expression again. So this is a fairly useful kind of two-way transition, because we can take an expression, convert it into a string, and then manipulate it, and then change it back into a different kind of expression. Because there's lots of commands you can use to manipulate strings. For example, if we take this string here, we can do string split. So we'll split this string wherever, for example, we see a 1. This is just a silly example. And what we've done here is to make a kind of list where we've cut the string wherever we've seen a 1. Now, one of the most useful commands in string manipulation is a command called string replace. So, again, if we take this, we can go string replace this, and we can replace every string, let's say every 1, with a 10, let's say. So you replace one kind of string with another kind of string. So we could do that, and then perhaps we could convert it back into an expression or whatever. Okay, so if one has a given string, like this, say, then you can just get the individual characters from it, like this. And that just gives you a list of little strings, one for each sort of character. Okay then, so now let's have a bit of fun with some strings. We're going to make some very complicated patterns with some simple programs, okay? So we're going to use nest list, and this is going to be our update. We're going to use string replace, operating on the string, and this is going to be the operation that we're going to do. Now, let's start off with 110, 110, 110. Let's do, say, 10 iterations. We want to visualize this in a better way. So let's write a little function now to convert something like this into a list of numbers, so we can use array plot to actually visualize. Actually, let's also just take the first 5 steps. It's easier that way. Okay, so this is the kind of thing we're playing with, and we want to be converting this into a list of numbers. So we'll write a function now. We'll call it convert. Takes in some input x, and what it does firstly, it gets a list of characters of x, and then it does a map so that if a particular character is equal to a 0, then it returns a 1, otherwise it returns a 2. Okay, so let's try doing this convert function on this. Okay, that's good. So we're turning these binary strings into lists of 1s and 2s. So now we can just do this operation on here. So here's our list, and now we just do a map where we apply this convert to each part, and then we can just array plot that. Okay, so we've got a visualization here of what's going on. The problem is that the string's actually grown too quickly for us to really see it properly. So we've got to be quite careful now about cutting down the string. So we just want to take the first 100 elements on the left and just visualize those. Here's where we have to be careful, because we better not try and take more elements than there actually are in the string. Okay, that ought to do it. Now we can take the first 10 iterations. Let's see how far Mathematica can handle it. Maybe 20 is pushing it a bit. Okay, and there we are. So what we're doing here is we're visualizing as looking at our original algorithm, which is basically this. We're visualizing the red blocks as ones and the purple blocks as zeros, and successive rows represent successive strings, and we're just repeatedly applying this string replace operation. It's pretty interesting. Starting from this initial condition, we get this really rather bizarre pattern emerging. I haven't done any analysis of this, but I think it's fairly interesting. Okay then, so that pretty much concludes things. Just to wrap up, I'll show you a very useful little command. So if we say cat equals 7, then notice that cat now becomes black. And if we call it again, of course it has this value 7. Now, programming like that can be kind of annoying because if you forget and then you use the word cat later, it can kind of mess up your code. So a really, really useful function is this thing called module. So within a module, you can define things kind of locally so that they have specific definitions inside that module, but outside of a module, there can be something else. So, for example, we could say that dog is equal to 9 inside here, and then we can do dog plus 4, and the output is 13. But if we look at dog outside of a module, it's undefined. Similarly, we can also say that cat is equal to 5 in here, and look at dog plus cat, and we get 14. So inside the module, cat has a value of 5. Outside of a module, cat has a value of 7. So it's like, for example, you can even, like, certain things in Mathematica are protected, like SQRT. That means square roots, okay? So in general, you're not allowed to redefine that. So I wouldn't be allowed to define a variable called square root equals 9. It wouldn't let me do that because it's protected. But it would be fine to do that within a module, I think. I think it should let me do this. Yeah. So basically, when you make one of these modules, you can define things in a very general way, but it's just contained within this little bubble. So that's a very useful little function. Okay then, so that's the end of my tutorial. Please like and subscribe if you enjoyed this, and tell me if there's other things in Mathematica that you'd want a tutorial about.